Hello, this is Raj Patel, and today we're going to be talking about ideal gas laws, and then we're going to be also getting into some gas stoichiometry. And this will be the last video ever you'll see of chemistry. So this is the final and last video. So we're about a few minutes away from end of chemistry. And so here let's talk about ideal gas laws. And so we've talked about combined gas laws, which is this formula you see right in front of you. P1 V1 over T1 equals P2 V2 over T2. And it says, this formula is used to calculate effects of changes in pressure, volume, and temperature. And the only side drawback to this formula is that we cannot change the number of moles. We cannot change it. And so, this does not include Avogadro's law, which states that, if we increase the number of moles, the volume will increase because we can't change the number of moles with using combined gas laws. So that is why we have this new formula we're going to talk about. And so far we've seen all these different laws, and these laws all come together to form this equation, which is PV over NT equals this gas constant R, which is the same ratio for every gas. And the ideal gas constant, which is R right here, is 0.0821 liters times atm per mole and Kelvin. So it's pretty much pressure and volume over number of moles and temperature, just like this. And so from that we derive this formula PV equals nRT just by moving NT to the other side. And so this is the formula we're going to be using. And the ideal gas constant tells us the units we have to use. So we have to have pressure in ATMs, V in volume in liters, number of moles and obviously number of moles, and then temperature must be in Kelvin. So remember, we have to use these 4 different units: liters, ATMs, moles, and kelvins. And so this is a new formula, and notice how it includes the number of moles, so we can change it now, unlike in combined gas laws where we couldn't change it. And remember, we cannot use any other units, so we have to use those 4 units. We can't use milliliters, mmHg, or kilopascals, grams, or Celsius. We have to use these 4. And so here, without further ado, we're going to do some calculations with this new formula. And it's pretty easy, so don't worry. So we have a 5-liter balloon is set at 0.855 atm and 25 degrees Celsius. How many moles of gas are in the balloon? So we first look at our formula, which is PV equals nRT. And remember, R is a constant, so it's always given to us. And so we have 0.0821 as R. So first, we have to, pull out what we have and plug it in the formula. So 5 liters is volume, so that goes with V. 0.855 atm is pressure, which is where P is. And 25 degrees Celsius, remember, convert to Kelvin to temperature, and we get 298. And then R is given, which is 0.0821. And so we have this all, and we need to solve for the number of moles. So think of algebra, and so we have to isolate n, so we have to divide these 2 numbers away to the other side. So we divide both sides by the right side, and so pretty much essentially we're dividing the left side by the right side, except for n stays over there. And so if we do this and type in our calculator, so 0.855 times 5, and then once we get that answer divided by the product of these 2, we should get an answer of 0.175 moles. And so that is it. There's no magic to this formula. It's pretty simple. And so now we have a second problem. What is the pressure of 0.435 moles of HE or helium gas in a volume of 8.12 liters and 0 degrees Celsius. So we need to find pressure this time. So again, we just pull out our formula, and remember R is a constant right here, 0.0821, and we need to solve for P. So we plug in what we have. So this is moles, 0.435 goes with N, 8.12 goes with volume, and then 0 degrees Celsius convert to Kelvin by adding 273, and that goes for temperature. So we plug in the following variables in their corresponding spots, and then to isolate P, we divide the whole right side by 8.12. So we first multiply 0.435 times 0.0821 times 273 and divide by 8.12, and if we do this, we should get a pressure of 1.2 atms. And so now we have question 3. A sample of aluminum chloride weighing 0.05 grams at 350 degrees Celsius and 760 mmHg of pressure occupies a volume of 19.2 milliliters. And calculate the molar mass of the gas. So this is a little tricky problem because we have an extra step here. And so this time it wants us to calculate molar mass, but we're still going to use a similar format, but we just have a special ending. So it essentially gives us temperature, pressure, and remember 760 we have to convert to atm, so it's 1 atm. And we have volume here, which we can convert to liters by moving the decimal place 3 places to the left or right. And it's 3 places to the left, definitely. And so we have our formula here, and remember R is always given to us, 0.0821. And so we write down and fill in what we have. So we have temperature here, we have our constant, number of moles we need to solve for, liters we converted milliliters to liters, and then 1 atm is 760 mmHg. And so once we have this, we can solve for number of moles by again dividing the left side by the product of the right side. And after doing that, we should get number of moles of 0.000375. And so remember, now we have to figure out the molar mass formula. And remember, the molar mass formula is the grams divided by moles. So in this case, it gives us the grams right here in the problem, 0.05. And then we just figure out the number of moles this gas takes up. And we figured out it's this very, very small number. So if we do these 0.05 divided by this very small number, we should get 133 grams per mole. So even though this problem seems a little complex, just go with what you know, and remember, molar mass, you have to know that it's grams per mole, and then we know our PV equals nRT. So we had three things, so we could solve for N, and just put the two pieces together. So once we solved N, we could have easily got to molar mass by dividing by grams per mole. And by the way, if you knew what this chemical was, it's aluminum chloride. So remember, ionic bonds have to balance out, so you could have figured it out just by doing that. But the whole thing is to know the formula and how to solve for number of moles and then go to molar mass and stuff like that. And so now, moving on, now we're going to be talking about gas stoichiometry. And trust me, this is the last time you'll hear me say gas stoichiometry. And so, so here we have a problem. The formula, sorry. PV equals nRT. And now we're going to talk about molar volume. And molar volume is the volume of 1 mole of any gas at STP. And so the cool thing is that at STP, every single gas has the same volume. And that, if you go and calculate, remember, STP is 1 atm, so that gives us pressure, 273 degrees Kelvin, or 0 degrees Celsius. We have their constant here, and remember it's 1 mole, so we have N, so we just solve for V. And if you do solve for V, it is 22.4 liters per mole. So it'll always be like this at STP. And so we can use this to find how much volume of gas we need in a reaction. So instead of using molarity, we're going to now be using molar volume. So think of it as another little tool in our stoichiometry problems. But remember, this is only an STP. So if the problem says STP, we can use this. If it doesn't, we have to go use this formula again, and we'll have some problems to practice that. So here we have gas stoichiometry with molar volume, and the volume of NH3 gas can be produced from reacting completely 5.6 liters of N2 at STP. So what is the volume? Sorry about that. And so remember, we have to ask what we need. So we need volume. So on the side, we can write liters of NH3. And we have 5.6 liters of N2. So we first write that to the side. And remember, whenever we do gas or any stoichiometry problem, we convert from whatever we have to moles, and then we go from moles to moles using molar ratio, and then we go to the liters or whatever of the other substance. So exactly what we're going to do. And because we know it's at STP, remember we just talked about 1 mole of gas is 22.4 liters. So because we know that, we can go from liters to moles knowing that. And remember, whatever's on the top of the first fraction goes on the bottom, so we need liters of N2 on the bottom, and whatever we want to go to, which is moles of N2, on the top. So we write 22.4 liters on the bottom because we know 1 mole is 22.4 liters, so 1 mole definitely goes on top. And so we can figure out how many moles of N2 5.6 liters is. So once we do that, we convert from moles to moles using what? And did you say mole to mole ratio? And you are in fact correct. So we get that from the coefficients in this equation. Whatever goes on the top goes on the bottom of the next fraction. So moles of N2 goes on the bottom. What we want to go to goes on the top. So we want to go to NH3, so moles of NH3 will go on the top, like that. And then we get the two coefficients of this fraction from the equation. So 1 mole of N2 goes on the bottom, 2 moles of NH3 goes on the top, like that. And so now that we're in moles of NH3, remember we're at STP and we want to go to liters, so we can use our volume, gas volume, or molar volume, I should say. And remember, whatever's on the top goes on the bottom, so moles of NH3 goes on the bottom, and liters of NH3 goes on the top. Remember, there's 1 mole for 22.4 liters. So we cancel out the moles, and now we're in liters. So this is the final product. So we just multiply all the top numbers and divide by the product of the bottom, and we should get 11.2 liters of NH3. So this is all and good, but there is a shortcut which is pretty cool. So when you're at STP, remember we convert from liters to moles and moles back to liters. And essentially these two fractions right here and right here are reciprocals. And remember, if they're reciprocals in math class, you've learned that they cancel out, so they're like opposites. So 22.4 and 22.4 essentially divide each other out. So, and then 1 mole on top and 1 mole on the bottom, they also cancel each other out. So these two fractions, the first one and the third one, essentially cancel each other out because they're exact opposites. So we can just get rid of them from this whole equation thing and just literally multiply the first substance by the mole to mole ratio and get to the second substance, just like that. So we could have just done 5.6 liters of N2 times 1 mole of N2, 2 moles of NH3 over 1 mole, so we could have done this, and then got the same exact answer so much more quicker So this is a nice strategy to help you speed up on tests and save time. So just use this strategy, but remember it's only an STP. This can only be used at STP, so just remember that. And so now you can try this one alone if you want, but I'm going to go through it. So if you want, you can pause the video right now and set up this whole thing. And so, what is the volume of O2 gas that is produced when 980 grams of KClO3 is decomposed at STP? So on the side, we can write we want volume, so liters of O2 off to the side. And we have 980 grams of KClO3, so that's what we're going to start off with. And remember, we always want to go to moles, so we can go to mole ratio. So we use grams, and remember, molar mass is what's used to convert from grams to moles. That's like your best friend when you're doing from grams to moles. And luckily, this PowerPoint gives us that the molar mass of KClO3 is 122.55 grams per mole. And remember, whatever's on the top goes on the bottom. So grams per mole, grams of KClO3 goes on the bottom. 1 mole goes on the top. And remember, we just get these numbers from the molar mass. So 122.55 grams of KClO3 per 1 mole. So grams will cancel, and we're now in moles of KClO3. So check step 1. Now step 2, we want to go from moles of KClO3 to moles of oxygen here. So we get these, we use a mole to mole ratio. And remember, whatever's on the top of this fraction goes on the bottom of the next, so we cancel it out. So moles of KCl3 goes on the bottom, moles of O2 goes on the top. We get these two numbers from the coefficient, so we have a 2 in front of KCl3, so 2 goes down here, like that. And then 1 mole goes for oxygen because there's an imaginary 1 out here. So now that we're in moles of oxygen, check, we're all good. And now we want to convert from moles to liters. So remember that we're at STP, so remember your good old friend 22.4 is going to be there to help you. So we want to convert from moles to liters, so we use that molar volume, so whatever goes on top goes on the bottom. So moles go on the bottom, and then liters will go on the top. And then so for every 1 mole, there's 22.4 liters. And voila, we are done. So now we just multiply all the top numbers and divide by the product of the bottom. And so, if we do that, we should get 89.6 liters of O2. And sadly, I'm sorry, I don't have a shortcut for this one. But the only shortcut is when you're converting from liters to moles back to liters at STP. But this one, because we were starting grams, they don't cancel out. And so now we're going to talk about one question with not at STP. So this is the only one. This is a weird one. So this is going to be a little extra step, but it's not much harder. Trust me. So what volume of O2 gas is produced from 490 grams of KClO3 at 298 degrees Kelvin in 1.06 atm? And so we want to, on the side of our head or on the side of the paper, you can write that we want to, we have volume of O2, and when it's not an STP, by the way, we have to use PV equals nRT somewhere in this conversion. And so off to the side, we can write that we want volume of O2 gas, so we can write liters of O2 off to the side. And then we have 490 KClO3, so that's what we're going to start with. And we're going to work our way slowly towards this PV equals nRT and then get their final answer. So here we have 490 grams of KClO3, and remember we want to go always to moles first, mole to mole ratio, and then back to what we need. So here we have grams, and remember molar mass is our best friend when converting from grams to moles. So we essentially divide by 122.55 grams, goes on the bottom. And once we get to a mole to mole ratio and then get to moles of oxygen, we plug in the moles of oxygen into this formula here, and we have these two other things so we can solve for volume. That's how we're gonna, that's like a essential like outline of what we're gonna do. So again, we put grams of KClO3 on the bottom, so grams cancels out, and then moles of KClO3 on the top, and 122.5 goes on the bottom, 55, sorry, because that goes with grams, and then 1 mole goes on the top. Now that we're moles of KClO3, that's all good, and now we want to go to moles of oxygen. So here we have 2 moles of KClO3 and 1 mole of oxygen, so these are going to be our mole-to-mole ratio, and whatever's on the top goes on the bottom, so moles of KClO3 on the bottom, moles of O2 on the top, the corresponding coefficients, so 2 moles of KClO3 and 1 mole of oxygen. And so now that we're in moles of oxygen, we just multiply the tops and then divide by the bottom product. And so once we do that, we should get about 2 moles of O2. And now we're ready for the second step, which is PV equals nRT. So now that we have moles, we know R is 0.0821, and we have temperature, which is given the problem, 298 degrees Kelvin. Hey, no converting. And then 1.06 atm. We can solve for volume, so that's how you solve for volume if you do not have STP. So we plug this into our formula, and we divide by 1.06, divide the whole right side by that, and so we do 2 times 0.0821 times 298, divide by 1.06, and you should get 46.2 liters. And that is how you do problems without STP. So remember, you just go work your way to moles, and then mole-to-mole ratio to convert to the other substance. And depending if it's at STP, we can go ahead and use molar volume. If it's not, we have to use this PV equals nRT. And that is how you do these types of problems. So, congratulations, you guys. You have just finished chemistry. So, this is the last video of chemistry. And I hope this helped you with throughout the whole year, and this video helped you learn. And please share these videos with any of your friends or anyone that needs help in chemistry. And if you have any questions or comments, you can please email me at mpatelbuccaneer@gmail.com. And thank you for listening throughout the whole year. And I hope this helped you and you did well in class. And so please give me feedback so I can, improve my videos. I might make more videos for other classes or something. So please help me. And I really enjoyed doing these videos. It really helped me review, and I hope it helped you review. And I hope you had fun while doing this like I did. And we'll see you later, and I hope you have a good day, and good luck in the rest of your high school career and on in life.